All right, guys, so what we're looking at here is a problem from 2019. This is a related rates problem kind of mixed in with a particular solution problem. But I figured I'd put it underneath related rates because we needed to look at that one a little bit, okay? And this is supposed to be done without a calculator, so just be aware of that. Problem says a cylindrical barrel with a diameter of 2 feet contains collected rainwater shown in the figure above. The water drains out through a valve not shown at the bottom of the barrel. The rate of change of the height of the water in the barrel with respect to time is modeled by, it gives us dH dt, with -1/10, and then the first thing that's kind of weird about this is it's the square root of h, where h is measured in feet and t is measured in seconds. Then we've got the volume of the cylinder with radius r, and height h is v equals pi r squared h. So it gives us that. Anytime it gives us some sort of volume or area formula, you're almost guaranteed that you're looking at a related rates problem. So here we go. Letter A wants us to find the rate of change of the volume of the water. So I've got v equals pi r squared h, with respect to time. So what that's asking us to do is to take the derivative of that equation. We're going to have to use the product rule between pi r squared and h. So I've got pi r squared, and then we multiply that by the derivative of h, which is dH dt, plus the h times 2 pi r dr dt. Now, once we have our derivative, it wants to know what it is with respect to time when the height of the water is 4 feet. So h equals 4. What we have to realize in this problem is the radius of this circle is never changing, which means dr dt is going to be 0. So all of this stuff right here is all 0. Then we're going to have plus, we've got pi times the radius is always 1. If the diameter is 2, the radius is always 1 in this problem, so I get 1 squared times dH dt, but we know that dH dt is equal to -1/10 times the square root of h. Well, h in this case is 4, so I just go pi times 1 squared multiplied by -1/10 times the square root of 4, and that is technically our answer in this problem. Okay, so I've got that as my answer. If you simplified it down, which you don't need to, but you'd get -pi/5. And it'd be cubic feet per second. So you don't need to worry about that too much. I mean, that's the units. You can tell because it's the rate of change of volume. So that one's not that bad. The second one wants to know when the height of the water is 3 feet, is the rate of change of the height of the water with respect to time increasing or decreasing? In other words, it wants to know, is this increasing or decreasing? So I need to take the derivative of that. So I'd get d squared h over dt squared. This is where this gets tricky. I take the derivative like I normally would, so I get -1/10 times, that's h to the 1/2, so the derivative of that is -1/2, or +1/2 times h to the -1/2. We're multiplying by that, and so we get that right there. But because we're taking it with respect to time, I need to put dH dt on the end. Now I know that looks a little weird, but you get -1/10 times 1/2 h to the -1/2, which I'm going to move that down to the bottom, make it h to the +1/2. And then we know dH dt is -1/10 times the square root of h. So I take 3 and I plug that in here, and with a so I have 3 everywhere I see an h. So I get 1/2 times the square root of 3 times -1/10 times the square root of 3. Those cancel out, times -1/10. You don't need to know that, you just need to know whether it's negative or positive. I get a positive number. It's actually 1/200. Because that number is positive, that means that the rate is increasing at that time. Again, that one's a little bit tricky, but that's how we do that one. Letter C says at time equals 0, the height of the water is 5 feet. So it almost like it's giving us like an initial condition. Use separation of variables. So I've got dH dt. Anytime we use separation of variables, that means we're moving one variable to the left-hand side and one to the right-hand side. So the dH dt, it's going to be over here. I divide by the square root of h, so I've got 1/h dH is equal to -1/10 dt. Then what we do is we take the antiderivative of both sides. So on the right-hand side, I get -1/10 t plus c. On the left-hand side, I move the square root of h up to the top, and I make it h to the -1/2. So when I take the antiderivative of that, I get h to the 1/2 divided by 1/2. So I've got that set up. So now, I mean, I can simplify that a little bit. I get 2 times the square root of h is what that looks like, is equal to negative 1/10 t plus c. I know at time equals 0, the height of the water is 5, so I get 2 square roots of 5 is equal to negative 1/10 times 0 plus c, so the constant is equal to 2 square roots of 5. If that's what the constant is, I plug that back in, so I get 2 square root of h is equal to negative 1/10 t plus 2 square roots of 5. Now I just need to get the h all by itself. So I divide everything by 2, and then I'm going to square both sides to get the h by itself. And that is what our answer is on this problem. So we found the expression. Now, just so you're aware, sometimes you might see it where it's not all divided by 2. We can add the 2 to both of those fractions individually. So I could have negative 1/20th t plus the square root of 5 all being squared, and that would be an equivalent term. And if you saw like an answer key, that's what it would look like. Anyway, hopefully that question made sense. If you have any questions about how we got those answers, because that one was kind of tough, please let me know.